Lesson 4.2, Graphing Quadratic Functions in Vertex or Intercept Form. In this lesson, we'll look at the other two ways you can write a quadratic function and how to determine our key features based on the equation type that you're looking at. Let's start with vertex form. Vertex form is going to look the most similar to the absolute value transformation equations from 2.7. It literally has all of the same letters. The only major difference is that instead of absolute value, your x minus h has a parenthesis being squared. But the a, the h, and the k will do the same things for the transformation that they did in lesson 2.7. Let's look at how to get the four key features down below to sketch our graph. As we think about determining our four key features, the vertex is actually going to be the easy step. Looking at the translation x minus h on the inside of the parenthesis and then plus k after, we actually use those numbers to determine the value of the vertex. Now for the h part, remember we have to think opposite signs. And for the k, it's going to be the same sign. And we'll look at a couple of examples on how to navigate that. And then the axis of symmetry, like standard form, is the same value as the h coordinate in the vertex because it has to be that vertical line. So for the axis of symmetry, the AOS, we know that the template is going to be x equals, and it's whatever our h coordinate is from up above. So whatever's here is down here. Now the y-intercept is where we have to be careful. The y-intercept is where we have to show work. So write work right here. We do plug in 0 for x, very similar to what we did in standard form, but now if x is on the inside with the parenthesis, we have to actually simplify and work inside out. So this is the only real major work you're going to show on this whole kind of set of problems or set of steps. Plug in x equals 0 and simplify. So it's not going to be the k value at the end. That's going to get you stuck a lot if you just assume that would be true. So you have to simplify that whole right-hand side. And then that'll be the y-intercept. Again, that's the most amount of work. And last but not least, your reflection point, just like we did before, take the y-intercept and reflect over your axis of symmetry. And that's all you do. And then also, if we need to create another table, we will. But if this is enough information to sketch our curve, we should be fine. Let's take a look at two examples on the right. For each quadratic function, state the form it's in, list the key features, then sketch the graph. And as always, we'll include our domain in our range. Taking a look at this first equation, y equals negative 1/2 times x plus 2 squared plus 5. Since it has that one parenthesis being squared, this is in vertex form. Simple enough. Our four steps then to get the vertex, we know that if it's x plus 2 on the inside, we have to go to negative 2 because it moves the graph 2 to the left. And then plus 5 on the outside means it will go up 5. That's literally how you get the vertex. So down below in your graph, please plot negative 2, 5, and put a dot. That's step 1. Now, step 2, your AOS, your axis of symmetry, is just the same as the x coordinate of the vertex. So we write x equals negative 2. And that's that dashed line that goes through the vertex. So I'm going to slide my graph up just a little bit and draw that in with my dashed vertical line. Like so. Arrows on the bottom and the top. All right, from there, now we have our work step, the y-intercept. Like I said, we have to actually calculate this one. So if we plug in 0 for x, I'm going to slide this back up so I can see my equation better. There we go. We're going to get y equals negative 1/2 times 0 plus 2 squared plus 5. We have to work inside out. So kind of like how we talk it through in class. Think if you can say it out loud with me. What's 0 plus 2? That's 2. What's 2 squared? That's 4. If we take negative 1/2 times 4 plus 5, well, negative 1/2 of 4 is negative 2. And negative 2 plus 5 would be 3. That means our y-intercept is 0, 3. Make sure you can calculate that with me. All right, so 0, 3, I'm going to put that point over here on my graph. And then last but not least, step 4, our reflecting point. Notice down here on your graph, see if I can come over here a little bit closer, zoom out on that a little bit. We're only 2 units away on that right-hand side. So if I count 2 to the, whoops, here we go, hang on. If I count 2 to the left and I go 2 in the other direction, my reflection point is over here on the right. So I'm just going to get rid of that extra. We don't need that. Okay, like so. All right, so the ordered pair location for that reflection point looks like it's negative 4, 3. So I'm going to go back up here to the top. My reflection point is negative 4, 3. Now, as I look at my graph, I think I'm going to want to make at least a table for at least one more ordered pair. So I'm going to draw my graph in over here. Let's look at what we already have. We have negative 2, 5. We have 0, 3, and negative 4, 3. So I'm going to go one more to the right. I'm going to go when x equals 1. I'm going to plug in 1 and see what happens. So just kind of, whoops, I didn't mean to shade that, sorry. I'm going to plug in 1 and see what happens. So if we go back up to the top, 1 plus 2 is 3. 3 squared is 9. Negative 1/2 times 9 is negative 4.5. Plus 5 puts us at 0.5 or 1/2. So at 1, I'm only up a little bit. And I'm going to reflect that to the other side, and that would put me right there. So it looks like my vertex is at the top, and I'm going to extend all the way down to the bottom of my graph. So I'm just going to draw a curve through those points, continue out to the left on one side with my arrow, and do the same thing on the other side. Being careful to not go straight up and down, but have your arrows at the bottom. Now, last but not least, we know that we need to add our domain and our range. The nice thing about domain, that's our free point. Let's take that. We know that we can go to the left and right forever using infinity notation, negative infinity to positive infinity. Now our range is going to be reflected of not only the variable in the equation, which in this case it's y, but now notice our arrows are at the bottom of the graph, so they go towards negative infinity. And that is smaller than positive infinity, so that has to go first. And we max out over on the y-axis over here at 5. So we max out at 5, and it can actually equal that value, so I'm going to put that in a bracket. And there you have your first graph in vertex form. All right, let's try the next one. Example B on the right kind of looks like vertex form, but some parts are missing. It's y equals x minus 3 squared. So notice there isn't a number out in front, but that's okay. Not every quadratic function has a number listed. Essentially, that just means that a equals 1. Whoa, hang on, sorry. That just means a equals 1, and that's okay. And then because nothing's written after the parenthesis, if you want that placeholder, let's put plus 0. That would be the k value. And now it kind of looks a little bit more like vertex form. Let's go through our steps. Step 1, let's get the vertex by doing the h and the k. So if it's x minus 3, that means the graph is going to translate 3 units to the right. So that would be positive 3. And because there is nothing written after, technically the y-coordinate of the vertex will be at 0. That's step 1. There's our vertex. Step 2, let's go ahead and find our axis of symmetry. And I'm just quickly going to zoom out so that as we start plotting all these things, including the vertex, sorry about that, forgot. We'll get that there, 3, 0. All right, carry on to step 2. The axis of symmetry, the AOS. Remember, in this form, and just like standard form, it's the same as the x-coordinate of our vertex. So it's going to be positive 3. Please draw that vertical dashed line in. edge to edge on your graph. Whoops, going right through here. Sorry. My pen that I'm using isn't being super cooperative right now. There we go. That looks a little bit better. And that's it for step 2. Step 3, the y-intercept. Again, we got to do a little bit of work on this one. For our y-intercept, we have to plug in 0 for x. So y equals 0 minus 3 squared. All right, so 0 minus 3 is negative 3. And negative 3 squared is positive 9, making our y-intercept 0, 9, almost all the way up to the top of our graph. And if we reflect that to the other side, notice it's 3 units away. I'm going to count 3 units away on the other side, and that reflection point is 6, 9. Notice our vertex is way down here at 3, 0, and we've got those 2 points up towards the top of the graph. I think that should give us enough information to sketch our parabola. So I'm going to go from my vertex and just kind of curve my way up to the right, arrow at the top, and do the same thing as best you can on the other side. Oops, I kind of missed that a little at the bottom. There we go. And there's our quadratic function for y equals x minus 3 squared. Now, last but not least, let's be sure to state our domain and our range. For the domain, get your free point, negative infinity to infinity. For the range, we're using y again. Notice with our arrows at the top, we need to look at that bottom number, and it looks like y's lowest value is 0. With arrows at the top, it goes up towards positive infinity. And that's the sketch for our graph of this quadratic function in vertex form. Our third and final form used for graphing quadratic functions is intercept form. And when we say intercept form, we're not counting the y-intercept in this. This is going to give us our x-intercepts. And what's unique about this form is we have 2 parentheses instead of 1. We start off with y equals, and we have an a, so very similar to what we had before. And now we have 2 parentheses, and we no longer use h and k. We now use x minus p and x minus q. That's the form for intercept form. Our steps for graphing, notice there are only 3 steps this time. And now you start by finding the x-intercepts. And we do this by setting each parenthesis equal to 0. So we set x minus p equal to 0 and x minus q equal to 0. And then we solve for x, and those are our x-intercepts. You'll get 2 answers, and that will be step 1. There's a little bit of work there, but it's not that much. The vertex is the second thing we find, and this is where we're going to have a little bit more work. Now we know that everything about parabolas is all about that symmetry. That's why we draw in our axis of symmetry. The vertex is going to be in between the 2 x-intercepts, and it should be symmetrical. So we want to have an ordered pair. To get the x-coordinate, we take our 2 answers from step 1, the p and the q, and we divide them by 2. That's finding the average, or the middle, between them. And that will be the x-coordinate for the vertex. For the y-coordinate, we do what we did in standard form. Plug x back into the equation. Oh, that's back in. Sorry, I don't know what was going on with that. There we go. We just plug x back into the original equation and then simplify. And there's your vertex. Last but not least, your AOS, your axis of symmetry, is always the same as the x-coordinate right here of your vertex. X equals p plus q over 2. And you'll already have that answer. So we'll save the 2 graphs on the right for class, but I wanted to give you these steps to give you more time in class to work. There's the majority of our notes for lesson 4.2.